This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Our next speaker is Snehal Raj from QCware. Please.
Can everyone hear me in the back? Okay. Thanks, Ed. Hi, everyone. I'm Snehal Raj. I'm a PhD student at Sorbonne, and I also work with QCware. Really happy to be here. I want to thank the organizers for getting all these amazing people in this room together in Melbourne. It's actually quite nice to actually meet in person the names that you have been reading in Google Scholar and Archive. Today, I would like to talk to you about training efficient density quantum machine learning. And this is a joint work with some of my fantastic collaborators here, Brian, Amin, Nishan, Natanj, Skander, and Irdans. Let me start out by giving the scope of this talk. I'll be considering the usual regime of parameterized quantum circuits, where we have some data. It could be either classical or quantum. Then we have a quantum model. I'm constraining this to be parameterized quantum circuits. And we train this model until we can get some good accuracy on any task. It could be prediction, generation, inference, right? Now, I want to make two key observations about this regime. The first observation is that to increase the expressivity of these QML models, we usually tend to increase the depth of the underlying ansatz, right? But increasing depth in general can lead to barren plateaus, and that might make the training hard. So recently, non-unitary QML methods using linear combination of unitaries or mid-circuit measurements have been proposed as a method of building more expressive models which can mitigate these issues. The authors of both these papers are in the conference, and I encourage you to read their papers. They're quite nice. The second key observation is regarding the trainability of these models. So classical ML models can scale to billions of parameters because of backpropagation scaling. By backpropagation scaling, what we mean is the additional overhead in computing the gradients is not much more than executing the models themselves. This was also mentioned in Dar's talk just before. But we see that in general, PQCs do not possess this scaling. So for a model with m parameters, if the classical complexity to compute the gradient is bounded by log m times the time taken to execute the model, for a quantum model, it will scale linearly with the number of parameters. All this was discussed in a beautiful paper from Google that I cite here. So in general, this can't be done, but so we need to look for proper families which have favorable scaling laws with gradient extraction. Now, given these two observations, I would like to motivate the density QML framework, where we'll try to balance the expressivity by introducing non-unitarity and the efficient gradient extraction. So the first, one of the canonical ways of implementing non-unitarity is the linear combination of unitaries framework. Here, what we do is we construct QML models which look like this, where they have they're a distribution over a linear combination of unitaries. So a protocol looks usually like this, where you load the alphas. Then based on the alphas, you control your unitaries, and then you do some post-selection to get a state which looks like the linear combination of unitaries. So this is very nice, and it has favorable properties with respect to expressivity, but something that we need to take care of is the success probability. Because we are doing post-selection, preparing such a state has a success probability attached to it that diminishes exponentially, usually exponentially with the system size. Next, because we cannot extract gradients from all families of circuit in general, one particular family that I would like to mention, and this will be important in this talk, is a recent paper from Xanadu that showed that gradient extraction from a commuting generator circuits is efficient. I'll explain what they meant by that. So you have an input state, you have a parameterized quantum circuit, and you have an observable. But if the generators of your parameterized quantum states commute with each other, and they either commute or anti-commute with the observable, then you have what is called a commuting generator circuit. For these circuits, they showed that it's very efficient to compute gradients. And why? Because you don't need to go gate by gate in a parameter shift kind of fashion and pay the price of m when you have m parameters, you can actually, because the observables commute, diagonalize this observables and then measure them all at once. So this has favorable scaling, but the price you have to pay is by having a commuting generator circuit. Now, in general, we won't have commuting generator circuit. So the authors in this paper decompose a general ansatz into commuting block circuits. So you can always decompose any ansatz into these blocks, where inside a block the generator is commuting, but across the blocks they either commute or anti-commute. What this does is the gradient now scales with the number of blocks instead of the number of parameters. You can assume that you have a constant number of blocks and then it will be fine. But as I said, the additional constraint here is across the generators, the generators need to commute. Sorry, across the blocks, the generators need to either commute or anti-commute. All right, so with that all motivation in mind, I would like to introduce the density QML framework. This framework proposes to train a distribution over linear combination of unitaries that can possibly balance trainability and expressibility. I'll give an example of how to implement this in practice. Let's say you have a k-sided coin. You flip a coin with alpha 1 probability. You apply the unitary u1. You flip it again. Maybe this time it lands on the kth side. With alpha k probability, you apply unitary uk. So this protocol can be summarized in this pictorial representation here, where you're applying an input state, you're applying a linear combination of unitaries. Note that this alpha is now a probability distribution, and then you measure the observable. This is the state that you will recover. So why is this nice? Notice that because the circuits are independent, we can extract the gradients for this model independently. Like you can compute the gradients for U1, you can compute the gradients for UK, and then sum them together with this probability distribution alpha and get the gradients for the entire model. So what this means is the gradient complexity of this regime will depend on the gradient complexity of the subunitaries. So we can take the commuting generator circuits, as I talked about before, and this entire framework becomes efficient in the gradient complexity. The cool thing now is that the generators need not commute or anti-commute across the blocks. Now, one might think that because we are not doing LCU, we might be less expressive than the linear combination of unitaries. So we have some results from randomized compiling literature. If you were in Kristen's tutorial on Sunday, he talked a lot about this. Randomized compiling is this strategy where you use probabilistic circuit transformations to mitigate coherent noise into stochastic noise. So let's say you have a target unitary here, and you have many strategies of implementing the target unitary. What they have shown is it's better to implement a probabilistic ensemble of multiple strategies than any individual strategy. We will use a result from randomized compiling literature to show guarantees for the expressibility of this model. Let's say you have a target unitary V, and you have corresponding channel that acts on the input state for that unitary. And there exists like k subunitaries that each has an error bound with the target unitary. If you have a distribution now that a linear combination of unitaries also has an error bound, let's say epsilon 2, then we can show that the density model won't be much worse than the LCU counterpart. So the first error that we have is the individual QML model prediction error. The second error that we have is the corresponding LCU model prediction error. And finally, we can see that the density QML model prediction error is not much worse. We have used the Hastings-Campbell mixing lemma here. All right, now for a concrete example, I'll take the example of the hardware efficient ansatz. The hardware efficient ansatz has this entangling gates, a bunch of CNOTs, and they have single qubit poly rotations as the parameterized gates. If you want to extract gradients efficiently, what you could do is you can easily break them up into the D subblocks, because in each of these subblocks, the parameterized gates commute with each other. So you already have that functionality. But you might say that I'm okay with paying a little more price, and I'm okay with the gradient complexity of what the model already was. It's, what you could do there is make it more expressive by adding multiple such models and get them in a density framework to enhance your expressivity. Before showing the results, I would like to draw a connection from classical ML literature. So one of the most prominent protocols that we see in large language models as of today is this mixture of experts. So in mixture of experts, they train sparse experts for different kind of tasks, and then they have a gating mechanism to choose which expert to deploy for particular task. In this example, you can see that the gating mechanism has chosen only 2 experts out of the many. This is very good because it helps train in a distributed manner. Again, Das talk about this, but it also has some favorable properties with respect to training and inference. So I'll now try to convince you that the density model looks like a mixture of experts. So let's say you have an input X. You first pass it through a linear layer and then a softmax so that you get a probability distribution over your alphas. And you can use these alphas to create a density model that resembles the mixture of experts. All right, so now this is a table from the paper where we did analysis for different kinds of ansatz family. We have the hardware efficient ansatz, we have an equivalent ansatz, some had Hamming weight preserving ansatz. And in all these, the crux is that if you take the original model and create a density model, you can either improve the gradient complexity, or if you keep the gradient complexity the same, you might be able to improve the number of parameters and therefore the expressibility. Moving on to numerical results. The first result that I want to show you is on this bars and dots dataset. It was the dataset that was in the original paper from Xanadu. So they have what is called like these bars, which have contiguous arrays of zeros and ones, and dots, which are alternating. And they add some noise. The goal is to classify if each image is a bar or a dot. You can see that this data set is translation equivariant. So they use a XX equivariant model where the ansatz respects the equivariance of the data. What we did is we constructed a density model where we had XX equivariant plus a YY equivariant model at once, and then we tried to see how it performs. On the left-hand side, I have the accuracy plotted against the training epochs. So what we did is we let the XX equivariant model train up to saturation, and then we started training the density model, which included the YY equivariant model as well. You can see that even though the sub-model had saturated, we were able to get a bump in the accuracy. On the right-hand side, I have the accuracy plotted against the number of measurement shots, and you can see that the number of measurement shots kind of follows the sub-unitary measurement complexity. We repeated this experiment with more classes of circuits that were considered in the original paper, some non-commuting model, QCNN, and for all the models, we saw that even though the original models had saturated, we were able to get a bump without much of a measurement complexity increase. Another data set that we tried on is the canonical MNIST data set. For this, we used a particular kind of ansatz called the orthogonal quantum neural network layers. We chose this because this is very easy to simulate as it operates in the unary basis. If you want to know more about this ansatz, please come and find me. I'm happy to chat about them. And we ran this on the entire data set. Now, we generated density models for these by splitting layers into commuting blocks. We have a couple of versions. One of them is the shallow version, and one of them is the deep version. And the results are as follows. So in the red curve here, I'm showing a model which has n squared many parameters. You can see that it saturates to an accuracy of about 60%. Then I train sparse experts, which only have n parameters compared to n squared. And you can see that they don't do so well, like they're not able to learn. But as soon as we combine them in a density fashion, we are able to recover the accuracy of the n squared model. This is good because we gain a lot by doing the density formalism and saving on the measurement shot complexity. So that brings me to my final summary slide. Increasing depth increases expressivity, but it also becomes hard to train. Efficient gradient extraction is not possible in general, so we need to look at specific model families. And density QML could be a new toolkit for expressible and trainable models. The paper is up on the archive, so I encourage you to go and read. And if you have any thoughts, comments, or suggestions, please feel free to contact me at my website. Thank you.
Thanks a lot for the nice talk. Questions? Yeah.
Hi, thanks for the very good talk. In some zoomed out way, I have the feeling what this density QML models you described are some sort of classical boosting of quantum weak learners. Is that correct?
I mean, there's still going to be a quantum model, But what we do is we can sort of have this probabilistic ensemble of them, where each individual unitary needs to be applied on the quantum computer, but you can select the probability distribution classically.
Yeah.
Okay, I want to understand the training efficient part. A lot of the training is being outsourced back to a classical device, correct? Because you're introducing the measurements.
I mean, it's the same classical hybrid quantum framework where you would train a PQC. But imagine that if you had a classical and quantum hybrid framework, you would combine both of them separately and create a model from them. Like the gradients still need to be fetched via the quantum hardware, but you would combine them into this classical probabilistic ensemble.
There's a question over here. There in the end.
Yeah, hi, great talk. So my question, with this probabilistic ensemble, if you have, is it not going to be that the very deep terms have, gradients that exponentially vanish, and then you've effectively got an ensemble of just the shallow components, and then that might be, very easy to classically simulate?
Yeah,
so that's kind of like what I find in my work as well.
Yeah, that's an excellent question, and we are thinking about this. So I think the question reframed is if we have shallow and deep circuits and we combine them, then the gradients might come from the shallow circuits alone, and then you fall into that trap. What I could suggest is that the experts in the classical literature usually have similar structure, and then we combine them together. So maybe you could think of it like you keep the same depth across experts and try to boost the training that way, instead of having a deep expert and a shallow expert and trying to train them.
That's good.
Yep, question right there.
So once again, in Jamie's work, we looked at this non-unitary terms, basically the cross between the shallow and the deep. Have you investigated that as well?
Yeah, we have investigated that, but not in the context of this paper. I think it's a little outside the scope of this, but I'm happy to chat and share some of the results that we have.
Any more questions? Yeah.
Hi, nice talk. Do you think that this work can make the training possible on the real hardware, or it's still makes sense to train on the simulator and then do the inference on the hardware?
I mean, yeah, that would be the goal of this work, but I think it's only a step in that direction. We would need a lot of more work and follow up to actually have something on the hardware. So I talked about the expressibility and the trainability. One of the things that I swept under the carpet was the classical simulatability. Because we are making these easy to train on quantum, it would also become easy to train on classical, right? So there's this spectrum of models that we need to keep hard to simulate and then combine in this framework to sort of make it useful. So it's an excellent question.
Okay, we have time for one more quick question if there is one. Okay, if not, let's thank Snehal again.